laws of physics. And it's a complete mystery in the conventional way of looking at the laws of physics as to why this is so. Where does mathematics come from? Where do the laws of physics come from? But if we think of the laws of physics as, and indeed of mathematics, as intrinsic to the universe, like the software on the great cosmic computer, if we think of it that way, then we have a possibility of explaining mathematics and physical law as part of a common package. They co-emerge. I should say that this is not my idea, that Paul Benioff, one of the founders of the quantum theory of computation, was the first person to suggest this notion, that mathematics and physics really, rather than just assuming mathematics exists and then plucking the laws of physics out of midair, one might hope that we explain the nature of mathematics and physical law from a common source. Now, I've said that I'm going to give a couple of examples where it matters as to whether we think of the laws as intrinsic to and software in the universe or Platonic. And there are two, well, first of all, let me tell you why there should be a difference. If we think of the universe as like a gigantic information processing system, then the striking thing about it is it's a finite system. You can actually add up the number of bits of information in the universe. It turns out to be 10 to the power 122. It's not a hard calculation, and there's not really any doubt about that number. So it's a huge number. For most practical purposes, it makes no difference. There's plenty of information there to go round, so to speak. The number, by the way, is enshrined in something that physicists call the holographic principle, which relates to Jacob Bekenstein and Stephen Hawking's concept of the event horizon area of a black hole being a measure of its entropy, which is related to its information content. I won't dwell on the technicalities. But there is a sort of deep reason why this 10 to the 122 comes from. So expressed informally then, the laws of software imply that there will be a sort of inherent fuzziness or wiggle room in the operation of the physical laws, simply because they don't have infinite fidelity. You see, so long as Mother Nature can compute in this transcendent Platonic realm of perfect mathematical forms, she can do so to infinite precision. That's what Newton assumed, infinitely precise clockwork mechanism. But if it's really a finite state system, then that's a fiction. We simply cannot invoke calculative routines in describing the world that exhaust its computational resources. What does it mean to say that we have a state of the world which cannot be even specified without more bits of information than can be contained, even in principle, in the entire observable universe? Are there such states? Well, there are indeed. And I'll give you an example, because it's a curious one. In quantum mechanics, particles can be entangled together. It's a technical term. I won't go into what it is, except you'll probably have heard Einstein's famous phrase, ghostly action at a distance. And it means that particles can be spatially separated, but linked in some way. The great hope of the quantum computing industry, which would represent an exponential leap over the conventional computing industry, is to entangle together a large number of particles, electrons, atoms, or whatever, to use the thing to compute. It turns out that an entangled state of just 400 particles already hits this 10 to the 122 limit. In other words, it's impossible to even specify, let alone predict the behavior of a state of more than 400 entangled particles. Now, for most people steeped in the Platonic tradition, they say, so what? You know, Mother Nature will be able to compute what these things do. But if you really think that the laws of physics are inherent in the universe, this limit of 400 entangled particles represents a problem. And I'm going to stick my neck out and say that I would predict that if we create such a state, that what physicists would call the unitary evolution of this state would break down. Something funny would happen. Now, seeing as that the industry has set its sights on 10,000 entangled particles, it could be of practical significance. And it's something that may be tested in the near future. So it could actually matter as to whether the laws are infinitely precise Platonic things or whether they're, as it were, in the universe. And I'm getting very near to the end now, in case you're getting a bit bored with this. The other circumstance in which it might matter is in the very early universe. When the universe was smaller, it could contain less information, and the fuzziness of these laws would have been correspondingly greater. So according to this view, the universe and its laws could have co-emerged with the laws sharpening over time onto what we see now from a sort of fuzzy beginning. And again, John Wheeler was there years and years ago. He said everything comes out of higgledy-piggledy. There are no laws, except the law that there is no law, and it's an emergent quality. So I've drawn very much upon his work, upon the work of Paul Benioff. I've mentioned Seth Lloyd, Andre Lindy, David Deutsch, and Rolf Landau have all contributed to this view, which I've woven together in my own personal manner, but components of it can be found among the work of other physicists. So lastly, well, how does this matter? How can we use this to explain the Goldilocks enigma, the existence of observers and beings like ourselves, and deep questions like why are we here and why is the universe bio-friendly? Is there a connection? Is the fact that the laws are, as it were, malleable and fuzzy in the past, can that be somehow used to explain the bio-friendliness of the universe that emerged? Well, I think it can, but I'm not sure how much time I've got. What I should probably do is to just say in a few words what I have in mind here, and then if there is time or in question time, I can show one or two slides to make it clearer. But I want to motivate it by just appealing to some work that Stephen Hawking published last year. When you apply quantum mechanics to the universe as a whole, which is what we're doing here, in the standard way of doing it, you dream up some sort of wave function for the universe, or quantum state for the universe, which would have been the state at the beginning, at the Big Bang, and then you evolve it forward in time using mathematics, and then you draw consequences of what branches of the wave function are here and there and so on. But Hawking points out that, of course, that's not the way we do science, not the way human beings enter into the equation. Human beings observe the universe here and now, and we infer the past from present observations. Now, quantum mechanics is perfectly time-symmetric. Now, any of you thinking Stuart Hameroff at this stage, stop. This stuff is okay. So the laws of physics are perfectly symmetric in time. So when we retrodict the past, just when we predict the future in quantum mechanics, there's a fuzziness and uncertainty. And the technical way of saying that is that the present state of the universe is an amalgam or a superposition of different branches, evolutionary branches of the wave function, all leading to this, all together leading up to this point. And so the act of observation is an act of selection or pruning of this different sort of multiverse of different branches. And so Hawking points out that there is a sort of backwards in time effect, but it's not a backwards in time causation. It's not that what happens now changes what happens in the past. It's just that what happens in the past has an inherent quantum fuzziness or indeterminism by the very nature of quantum mechanics. And that observations made now resolve, in part, that ambiguity in the past. Now, this is not in doubt, and I could show some experiments that have been done to confirm it on a small scale. This aspect of quantum mechanics, weird though it is not in doubt. It's a sort of non-locality, which is across space, but also across time. So it's not a question of sending information or physical effects back into the past, but it's an effect of acknowledging that the past is not completely and totally defined until we make observations and resolve that ambiguity. And all I'm suggesting, that's the part that isn't radical. It sounds radical, but that I think is accepted by most physicists.